Okay, I'm going to continue with a review of material on the second part of the module, and as with the earlier review, this is intended to give some advanced preparation for the second class test, which will involve the subjects of calculus and complex number theory. As with the previous review lecture, I'm going to give some examples of typical sorts of questions, but I'm not going to go through solutions to them in this lecture. Those questions that I'm presenting, those will form part of one of the tutorials, and you'll have an opportunity to work through those for yourself. Okay, so calculus. What did we see when we studied calculus earlier? We saw the background to what is called differential calculus, the motivating problems and how those developed. We saw that calculus is a method for studying particular behavior of functions. We looked at the relationship between calculus and what are called optimization problems. We developed our basic single variable idea of calculus so that it can be applied to functions that depend on a number of different variables. I gave a very brief overview of integral calculus. We went on to look at complex numbers, and we saw, first of all, how this notion of complex numbers arose, because there are certain polynomials with real coefficients whose roots, however, could not be expressed as real numbers. We looked at the different representation forms that have been used to describe complex numbers. We looked at operations on complex numbers, and this is new material this year. We looked at the extensions that are required to classical calculus in order to apply those techniques to the complex arena. We looked at also, very importantly, a number of quite important applications in computer science of complex number theory. So for differential calculus, you have to be aware of, you have to be comfortable with the following topics. You have to know what a line function is and the attributes of a line, so things such as gradient and offset. You have to be aware of what the first derivative is actually describing as a gradient of a line touching a point on a particular curve on a graph of a function. You have to be aware of how we use first derivatives as a means of discovering the critical points of a function, and indeed what we mean by a critical point. How those points are classified using what I call the second derivative test. And the idea of how the basic single variable notions in calculus are developed to this idea of what I call the partial derivative, and how partial derivatives form the background to one method of solving optimization problems when we have several variables. You do not have to memorize standard rules for differentiating functions. If those arise, if you need those, look them up. They're given in the lecture notes, they're given on the slide, they're given in the textbook. There's no need to commit those to memory. Look them up. So typical example questions you might see. Once again, I'm not going to run through those in this lecture. You should work through them as practice questions in the tutorial material. So one thing you might be given, a typical question I've asked, is you're giving a starting coordinate and a final coordinate, and you're asked to determine what the gradient of the associated line is. A very similar question for a particular line. You may be asked to determine the corresponding value for a horizontal position relating to a vertical position. In the area of differential calculus, you may be given some particular function and you're asked to find the expression for the critical points of that function. Moving on to integral calculus, you have to be aware of how this notion of integration is an important tool, how it arose as a means of solving area measurement problems. You ought to be aware of how integral calculus is related to differential calculus by this idea of what I call the antiderivative of a function. You have to know about the distinction notationally between definite and indefinite integrals. You do not need to know about the development of integral calculus as it applies to measuring lengths or to measuring volumes. You don't need to know about these creative methods such as integration by parts, which some of you may have seen at school. And as with differential calculus, do not try to memorize standard tables of integration rules. Once again, look those up if you need them. So a typical sort of question that arises, you may be given an indefinite integral, something of this form, and what you're asked to do is to rewrite that indefinite integral as the sum of two indefinite integrals. And having done so, you may be asked to actually find what the integral is, to compute that integral. What about complex numbers? So you need to be aware of the different attributes of complex numbers. So things such as the fact that a complex number consists of a real part, an imaginary part. It is an object called its phase, which is an angle associated with it, that a complex number has a particular size and how that size is defined. You have to be aware of the fact that there are many different methods for representing complex numbers. You have to be aware of the basic operations that we saw can be carried out on complex numbers. So these are things such as adding two complex numbers, finding the modulus, the size of a complex number, this notion of complex conjugate, how to multiply two complex numbers, how to divide two complex numbers. It's also important that you're aware of this very important idea of the primitive roots of unity. You should have some sense of the extensions that are needed to classical calculus in order to apply it to complex numbers, in order to apply it in the complex plane. And most importantly, you have to be aware of the fact that complex numbers aren't just some theoretical abstraction. They have very important applications in computer science. So complex number forms, complex number operations. The main attributes, let me say again, this notion of the real part of a complex number, this idea of the imaginary part of a complex number, this notion of size, and this notion of phase. the different representation forms we saw. So there's a standard form. We have this idea of representing a complex number as a matrix on an Argand diagram, this polar coordinate form, and the Euler form of a complex number. We saw that the addition of two complex numbers, the multiplication of a complex number by a real constant, these are just analogues of the operations we saw with two vectors. Multiplying two complex numbers just involves expanding the two standard forms, written like this, but we use the property that this object I that we've introduced, when we square it, that gives us the outcome -1. Division involves exploiting properties of the complex conjugate and complex number size. Primitive root of unity, this is an object, we take a complex number, we raise it to a particular power, and the outcome of that computation is the real number 1. So again, some example questions you might see. You may be asked, given some selection of complex numbers, to give the equivalent polar coordinate or Euler form for those standard forms. You might be asked to compute the product of two specific complex numbers, such as this case. You might be asked to simplify expressions involving complex division. You may be asked to apply particular complex number sequence computation. So you're given some complex quadratic function definition, and you're asked to find the value after iterating that function some number of times. For calculus in the complex plane, one thing you should be confident about doing is applying what I called the Cauchy-Riemann functions to determine if a particular complex value function can be differentiated. Once again, you do not have to memorize those conditions. You should look those conditions up if you're not sure about them. The important technique is to be able to apply them, not to commit them to memory. You should be aware of the background to integral calculus in complex valued functions. So ideas such as what I call the contour integral, what I call the line integral. So you need to know about how you describe the function that's relevant to what I called a parameterized curve between two distinct complex numbers. You're not expected to be able to apply the integral theorem as it occurs in complex number analysis, but you should be aware of why it's important in computer science, or rather in a particular specialist area of computer science. So an example questions you might see. You might be asked to state which of a number of functions are differentiable according to the complex analysis concept of differentiability. So in other words, to state which of some number of functions actually satisfy the Cauchy-Riemann conditions. You might be asked to find a particular complex integral between 2 points by you finding a parameterized curve which connects those 2 points. You'll have to know about applications in computer science, so it's important to be aware of the significant uses of complex numbers and the supporting theory from complex numbers as they arise in computer science. So these are things such as the use of quaternions in advanced computer graphics, the use of integral calculus and complex number theory in analysing algorithms, particularly in average case studies. Ideas such as a Fourier transform, ideas such as the application of complex number theory in this area of AI called computer creativity. Now, some of those techniques you'll meet next year. So in particular, in advanced graphics, you'll meet the idea of quaternions again. In the final year of study, a number of these have formed the basis of final year project work. So one of the areas which I've offered final year projects in for the past few years has been in this field called computer creativity. And so there you'll need to have some basic understanding of how complex numbers work. So that concludes our review of the second part, and those topics will form the basis for the second class test.